This short slideshow will explain how rocks change chemically during metamorphism. Metamorphism is the process by which rocks change due to high temperature and pressure, and for the most part is a closed system process. That means that whatever elements are present in the protolith or parent rock are also present in the metamorphic rock. When the protolith is compositionally rich, like this shale, there are many chemical ingredients that can be combined into minerals, and it's possible and likely that the metamorphic rock will incorporate them into different minerals. For example, in the shale, the ingredients are made into quartz, different types of clays, and perhaps some iron oxide minerals. While in the garnet schist, the same chemical ingredients are combined into quartz, feldspar, muscovite, and garnet. Both rocks are composed of the same elements, it's just the way they're apportioned into minerals that's different. The one exception to the closed system rule is volatile elements, especially H2O and to a lesser degree CO2, which often leave the rock during typical regional or contact metamorphism. The reason is simple. These volatiles typically occur on the high temperature side of metamorphic reactions, like this one, and thus are produced during metamorphism. Being fluids, they are mobile and low density and immediately escape the rock. The general rule then is that during progressive metamorphism, rocks contain less and less volatiles. A compositionally simple protolith, like limestone, has many fewer chemical ingredients to work with. In fact, a pure limestone contains only calcium, oxygen, and carbon, and there's only one way to arrange these elements into a mineral under normal crustal conditions, as either calcite or aragonite, the polymorphs of CaCO3. Thus, the protolith limestone contains nearly pure calcite, and if we expose it to high temperatures and pressures, it will change into the metamorphic rock marble, which also contains nearly pure calcite. The only difference between the limestone and the marble is the size and shape of the crystals. In marble, the calcite crystals are large and interlocking because it has recrystallized. It makes little sense to think that the limestone with only calcium, carbon, and oxygen could transform into the garnet schist, which contains silicon, aluminum, iron, magnesium, and other elements that the limestone doesn't have. However, adding a little bit of quartz and dolomite to limestone changes things considerably. These minerals are common in real limestones, producing what geologists call a dirty limestone. The quartz adds the chemical ingredient silicon, and the dolomite adds the chemical ingredient magnesium. And now there are many more minerals that can be made with combinations of calcium, silicon, magnesium, carbon, and oxygen. As a result, when a dirty limestone is metamorphosed, it typically grows new minerals like magnesium-rich micas, amphiboles, and olivines. These minerals couldn't grow in a pure limestone, which lacks both silicon and magnesium, but can in the dirty limestone. This is why so many commercial marbles, used for things like countertops and building stones, are full of swirls of color. The swirls represent the minerals formed during metamorphism from the chemical impurities in the limestone. In some environments, metamorphism is carried out by hot circulating water. The circulating water adds H2O to the rock chemically, causing hydrothermal metamorphism. A good example of hydrothermal metamorphism occurs on the seafloor around mid-ocean ridges. Circulation of seawater, driven by heat from a shallow magma chamber, causes the ultramafic rock peridotite to transform into the metamorphic rock serpentinite. Serpentinite is a rock composed of essentially one mineral, serpentine, which is a clay mineral containing chemically bound H2O. Some rocks, especially basalts, may experience hydrothermal metamorphism when they're near the surface, and then experience regional metamorphism later in their lives when they get buried deeply or caught up in a mountain. Water may first be added to the rock during hydrothermal metamorphism, and then progressively driven away during the higher grade reactions that occur at higher temperatures and pressures during regional metamorphism. Finally, in some unusual environments, metamorphism may be accompanied by fluids that are rich in dissolved chemical components like silicon, aluminum, iron, and magnesium. These fluids are called chemically active fluids and can cause what is called metasomatism. Metasomatism is metamorphism accompanied by chemical change and is the exception rather than the rule. Because you're introducing new chemical ingredients, the possibilities for the metamorphic rocks are endless. You are no longer constrained by the chemical ingredients present in the protolith. In this example, the skarn rock contains large crystals of amphibole and olivine in addition to calcite and dolomite. The The silicon, magnesium, and iron needed for the amphibole and olivine were brought in by the chemically active fluids. Skarns often form around igneous bodies. As minerals crystallize from a magma, components that can't easily get incorporated into minerals get driven into the residual liquid. H2O is one of these components that prefers to reside in magma, so the last gasp of fluid remaining before the magma is completely crystallized is often a supermobile, water-rich magmatic fluid that can seep into surrounding rocks and alter them. As a result, igneous bodies are sometimes surrounded by a shell of skarn rocks.